Let's take a look at example 4. We're asked to find f prime of x for f of x equals the square root of x, and then we're going to use the derivative to find the slope of the graph of f at the following points 1, 1 and 4, 2. And we're also asked to discuss the behavior of the function f at 0, 0. So to find f prime, right now we're using the limit definition. We know that f prime of x is defined as the limit as delta x approaches to 0 of f of x plus delta x minus f of x, all divided by delta x. This is going to be equal to the limit as delta x approaches to 0. Here the function is simply the square root function. So this is a pretty nice one to work with. F of x plus delta x is simply going to be the square root of x plus delta x minus f of x, which is the square root of x, and then all divided by delta x. Again, my recommendation I gave earlier still stands. It's a good idea to put grouping symbols around the first part and the second part in your numerator. However, since we only have one term for each of our function evaluations, it's not entirely necessary. At this point, we want to see if we can find this limit. Now, if we tried direct substitution, if you plug in 0 for delta x right now, what we would get would be the following. This would be the square root of x plus 0 minus the square root of x, all divided by delta x, all divided by 0, which would be the square root of x minus the square root of x over 0, which would give us 0 over 0, which was our indeterminate form. Again, the helpful hint I gave earlier, you know you're going in the right direction if ultimately we should be able to do something to get that original delta x in the denominator to cancel. Well, this is similar to some of the limits we saw back in Chapter 2, where one of the fundamental ideas we have is we can try to rationalize either a numerator or denominator. In this case, we're going to rationalize the numerator. We can multiply top and bottom of our main fraction by the conjugate of that numerator. That's going to be the square root of x plus delta x plus the square root of x. And we're going to use this to rationalize our numerator. This will be equal to the limit as delta x approaches to 0. Leave the denominator in factored form. We weren't really trying to do anything with the bottom, so I'll leave it unmultiplied out. And then in the numerator, if you want to, it's up to you how you want to handle this. You could, distribute it out, first, outer, inner, last, all that good stuff. Or by recognizing that the product of sum and difference is simply the difference of the square of the two terms. That's what I'll do. This is equal to the limit as delta x approaches to 0 of the square root and the square cancel. So we get x plus delta x minus, again they cancel there, so x. We have delta x times the square root of x plus delta x plus the square root of x. And now that the numerator has been rationalized, we have some like terms that cancel. This positive square root of x, this positive x cancels with this negative x. This is equal to the limit as delta x approaches to 0. We now have delta x all divided by delta x square root of x plus delta x plus the square root of x. And now the delta x's cancel. So this cancels with this. And we're going to have the following. We have a 1 up top. So this is equal to the limit as delta x approaches to 0 of 1 divided by the square root of x plus delta x plus the square root of x. This is the step that follows directly after our delta x canceled. So now we should be able to take the limit. Everywhere you see a delta x, plug in 0. So this is going to be 1 divided by the square root of x plus the square root of x, which is 1 over 2 square roots of x. So the derivative of this function, the derivative of the square root of x, is equal to 1 divided by 2 square roots of x. So that's the first part. They also ask us to find the slope of the graph of f at the points 1, 1 and 4, 2. Let's do that. That comes from the derivative. Again, if you hear that buzzword, slope of the tangent line, slope of the curve, that for us is synonymous with the derivative. So f prime, this is at x equals to 1. If I plug 1 into the derivative, we get 1 divided by 2 square roots of 1, which would be a half. So the slope of the curve at 1, 1, that has a slope of a half. At 4, 2, that is a point with an x value of 2. F prime of 4 is equal to 1 divided by 2 times the square root of 4. That's going to be 1 over 2 times 2, which should be 1/4. So at the point 4, 2, the slope is going to be 1/4. If you're curious, or if you wanted to kind of, again, get some intuition, let's take a look at the graph of this function and see kind of like what's happening. So we have the point 1, 1. We have the point 4, 2, and this is our square root function. It looks like this. At the point 1, 1, if I draw the tangent line there, you would see that the tangent line is going to look like this. And that line that's in green has a slope of 1/2. If we go a little bit to the right, so at 4, 2, notice if I draw that tangent line, it's going to look like this. That line has a slope of 1/4. And if you're comparing the numbers, 1/4 is less than a half, which makes sense because as we move further to the right along the square root function, if you remember the graph of it, it kind of gets flatter and flatter and flatter. And so as we go further out to the right, the square root function rises really, really slowly. And so that's why we kind of see these small rates of change. There's another question. We haven't quite finished this problem yet. It said, discuss the behavior of f at 0, 0. So if I tried to ask the question, what is the slope of the square root function at x equals to 0, I could try to plug that into my derivative. Here x would be 0, but we would get that f prime of 0 would be 1 divided by 2 times the square root of 0, which is 1 over 0, which is undefined. Not only is it undefined, but from what we saw in section 2.5, whenever you have a non-zero number divided by 0, that would indicate an infinite limit. And sure enough, if you look at what's going to happen as we approach 0, those tangent lines, let me start to draw them, would be getting steeper and steeper and steeper and steeper, so much so that at x equal to 0, the square root function would actually have a vertical tangent line. So x equals to 0 would be the vertical tangent line for the square root function at x equals to 0. Let's take a look at another one. Let's find the derivative with respect to t for the function y equals 2 divided by t. So here we're using the y notation. So we're going to be looking for the derivative, which is going to be y prime of t. So this is going to be equal to y prime of t is going to be equal to the limit now as the change in the independent variable. This is going to be the limit as delta t goes to 0 of, let's call it, I guess, y of t plus delta t minus y of t all divided by delta t. this will be equal to the limit as delta t goes to 0. Here, for this function, it's just a single term. So if I plug t plus delta t in, I just get 2 divided by t plus delta t minus y of t, which is just 2 divided by t. And that whole thing should be all over delta t. Again, we can't evaluate the limit quite yet. If you try to plug in delta t, you'll get 0 divided by 0. So we need to do something in order to find this limit. And the analytical technique we're going to use this time is we're going to simplify this complex fraction. So I'm going to take the main fraction, the main numerator and denominator, and I'm going to multiply them by the LCD of my subdenominators, which is like my second order denominators. The LCD of the terms t plus delta t and t by itself is just going to be the product of the two. It's going to be t times t plus delta t. And if we do that, that should help us to simplify the complex fraction. Some of you may have learned other ways to simplify complex fractions. In particular, another approach you could do to do this would be to combine the two terms in the numerator by getting a common denominator and then doing the keep change flip. That also works. But let's just kind of go ahead and continue here. This is going to be equal to the limit as delta t goes to 0 of, in the main denominator, I'm going to leave it alone. I'm not going to distribute it out. I'm going to call it a delta t times t delta t. And in the numerator, I need to distribute this quantity into both terms. When we distribute it to the first term, the t plus delta t's cancel, and so we're just going to get a 2 times t. So we have 2 times t here. Subtract, if I come over here, when we distribute it to the second term, notice that the t's cancel, and we're left with 2 times t plus delta t. And now what that's done for us is that has simplified this complex fraction. This is going to be the limit as delta t goes to 0 of, distribute the sign in the numerator, we get a negative 2t minus 2 delta t all over delta t times t plus delta t. The next thing that will happen is in the numerator we have a 2t and a negative 2t. Those will cancel. So this is going to be equal to the limit as delta t approaches to 0 of negative 2 delta t divided by delta t times t plus delta t. And now the common factor of delta t cancels, so this delta t cancels with this delta t. So we have the limit as delta t approaches to 0 of, let me write it elsewhere so we can save a little space here. So this is the limit as delta t approaches to 0 of negative 2 divided by t times t plus delta t. And now we're in a spot where we should be able to plug in the delta t for 0. We're going to get negative 2 divided by t times t plus 0, which is going to be negative 2 over t squared. So there we have it. We found our derivative. If the starting function was y equals 2 divided by t, then y prime is going to be negative 2 divided by t squared. That's the derivative. That's y prime as a function of t. One of the next things we're going to talk about is differentiability and continuity, as well as some of the other forms of the derivative. You might see this definition of the derivative written differently. In particular, some people don't use the delta x approach. Sometimes you'll also see it written with like an h. Many books and some authors will say the limit as h approaches to 0 of f of x plus h minus f of x, all divided by h. This helps some students because oftentimes there can be some confusion between an x and a delta x term, which are two entirely completely different variables. If you have had some familiarity, or if you prefer this alternative definition of the derivative using h instead of like a delta x, by all means feel free to use it. It's the same definition. Yet another alternative definition is we could define f prime of c to be the limit as x approaches to c of f of x minus f of c, all divided by x minus c. And when we write this, as we saw back in chapter 2, this is a limit that doesn't have any subscripts, or excuse me, any superscripts. So it's presupposing that both the left-hand limit and the right-hand limit exist and are equal to each other. Okay. If that's the case, so if this derivative exists, then the following left-hand derivatives and right-hand derivatives will be the following. The derivative on the left-hand side as x approaches to c is going to be this limit, but it's the limit as x approaches c from the left. And the right-hand derivative of f at c is going to be defined as f prime subscript positive sign c, which is simply the limit as x approaches to c from the right of f of c, x minus f of c divided by x minus c. So much like how we had left-hand limits and right-hand limits, we have a left-hand derivative and a right-hand derivative. Okay. This will also allow us to now kind of define differentiability on a closed interval. We would say that a function is differentiable on the closed interval a to b if it's differentiable at every point in the interior. So if it's differentiable at every point inside a comma b, and if you also have a derivative at a, which technically would be a right-hand derivative, and if you would have a left-hand derivative at b. So differentiability in a closed interval means differentiability in the interior plus differentiability at the endpoints. We will go over this next, but we're going to look at the left-hand and right-hand derivative to see what's going on with the absolute value of x minus 2 at x equals to 2.